Hello everyone, this is Fabien Paillusson here. This is a great pleasure to give this public lecture for the University of Lincoln Science Week 2021. And what I'm going to talk about today is a very simple question. In fact, is a vacuum empty? And I want to provide here a modern physics perspective about it. And then we are going to see, whether vacuum is empty or not according to these perspectives. So first we need to clarify a little bit what we mean about vacuum. So a vacuum here would be an isolated region of space. So it has to be somehow limited in space, and usually inside it there are stuff that can be acted upon, right? So it can be a substance that is in there, or anything you can imagine. Now, once you've got this, then you've got a tool or a device that enables you to suck, if you will, this substance which is inside, or this stuff inside this particular region of space. So upon doing so, you will do this and you obtain a vacuum. Okay, so essentially, if I summarize this particular picture, you get that you've got things, then you remove them. Okay, so that's a vacuum. Now, what do we mean by empty? That's more of a philosophical question here, and basically it means that there is an absence of something. Okay, so that's what empty really kind of means. Now, you've got this usual question, which is about the glass being half full or half empty. Now, what we can say about this is that the glass may be half empty of water, right? So it's of something. So it may be empty, half empty of water, but it also actually always filled with something, because there is air around it. So the actual glass is always filled, but only half of it is filled of water, and the remaining half would be filled with air. So the thing here is that what is nice when we've got this idea of empty of something, we can then try to conceive a glass which would be completely empty of any matter content. Okay, so that's what at least we can conceive of. So once we've got these two definitions, what we can say is the following. If we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Okay, so that's what I'm going to discuss today. If we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Now, if no, then what that means in practice is that current physics may be able to address the question of a physical nothing. So if there is something, if you will, that can be removed, so that there is nothing left, if you will, for physicists to talk about, then there is somehow a conception of physical nothing. Now, if the answer to that is yes, okay, so if you take away all that can be removed, but there is still something to talk about, then what that means that current physics doesn't support the idea of an experimental situation which would be identifiable to a physical nothing, where basically there is nothing left to talk about. Okay, so that's what we are going to do today. Now, for sure, this is not an easy question to reply. So in fact, in 2012 there was a debate, so I think it's still quite recent, at least 2012, it's almost 10 years now, and that was between Lawrence Krauss and David Albert. Now, these two gentlemen are actually experts in their own right in quantum mechanics, and they strongly disagreed on basically these notions of vacuum and whether there would be something to talk about. Now, there is a strong disagreement here, and the strong disagreement between these two professionals of quantum mechanics and physics in general was about nothing and what you mean when they mean nothing. Okay, now it turns out that in this particular talk, I'm going to focus not on what these two gentlemen actually disagree on, but in fact what they would agree on. So the point here is that we are trying to answer on the fact that regardless, okay, of their disagreements, we can focus on the definition of a vacuum where both of these experts would actually agree on. Okay, so that's what I'm going to look at in this particular presentation. So that's what I'm going to mean by modern physics. So I told you that it was a modern physics perspective at the beginning of the lecture, and that's what I mean by a modern physics perspective. It's basically where these two experts are going to agree on this notion of modern physics perspective. So let's start with trying to define and see how physics talks about vacuum. So first of all, let's imagine you've got a chamber which is made of, I don't know, glass or something, which is isolating a region of space, and basically it's actually filled with air or a particular substance. Okay, so the thing that you can do to find out whether it's actually filled with a substance or not is actually make sound travel through it. So you take a microphone or a megaphone or anything like this, then you send sound waves through them, and then if the actual sound waves do propagate through this particular cavity or or chamber, then that means that there is a substance that enables the travel of this particular sound wave. Now, if you empty the box of this sound carrying medium, okay, so that's what I'm doing here, then upon essentially shouting at the box or sending a sound, essentially nothing is going to traverse the actual chamber, okay, and that's because the sound carrying medium has disappeared. Now, because the sound cannot propagate further, that's a way to identify the absence or the empty character of the box with regards to the sound carrying substance. Now, it turns out that this is an actual experiment which was performed by Robert Boyle and which was reported in an article of his or treatise of his, which was New Experiments in Physico-Mechanical Touch the Spring of the Air and its Effect. And here this is a representation, when you've got the link if you want to get there. It's a beautiful representation of the vacuum chamber device which was developed and used by Boyle in this instance. And he did actually prove, if you will, to his peers that he managed to obtain vacuum precisely by showing that the sound did not travel anymore through the chamber. Okay, so once we're there, then we say, well, there is something that kind of remains, right? And in fact, you can ask yourself, well, how do I know whether it's completely empty or not? So let's continue our use of waves to find this out. So if I actually use a lamp torch, then I'm going to shine light through it, and then the light is going through the actual chamber. So it's traversing through, and then I can see the actual light even if I'm across the chamber. Okay? So what that means here is that it seems that there is something left for light to travel into, which is inside the box. Okay? Otherwise, by analogy with what we have with sound, then in principle light wouldn't be able to travel. So that's where we are essentially. So now that we want to talk a bit of light, then what I'm going to do here is provide first, for the physics of propagation of light, I'm going to provide a 19th century explanation or interpretation of how light travels, and it's related to electricity and magnetism. Now, for the most part, this is how we need to this is how modern physics understand light travel. Okay, Be it for antennas or optics in general, you would get something like what we are going to discuss. Now, before discussing anything here, I'm going to focus on the electrical character of light propagation. And it's just because I don't have the time here to also go on to the magnetic aspect as well. Now, you simply need to imagine that it's the same thing as what I'm going to show, but just somehow in a higher dimensional space or with a more complicated object, okay? But at the end of the day, like the basic stuff is going to be in what I'm going to present. Now, electricity here, we need to summarize, a little bit what electricity is about so that we are on the same page to move forward to understand light propagation and then, vacuum related to light. So here we imagine like a spherical object that can carry electric charge, okay? So that's represented by this dot here. And the color code that I'm going to use is that this is going to be green if there is zero charge, then this is going to be red if there is a positive charge, and then it's going to be blue if it carries a so-called negative charge. So it's as if you had three types of charge, if you will. Now, the thing is that on top of this, there is some rules to be followed. So if you have, for example, next to each other a negative charge and a positive charge, then the rule is that they are going to attract each other. Okay, so opposite charges attract each other. The second rule is that if instead of a positive charge you put a negative charge next to a negative one, then they are going to repel each other. So the rule here is that like charges repel each other. The same would be true if you had a positive charge with a positive charge as well. So these can graphically be represented by plotting a field of arrows showing the direction of the force on a hypothetical positive charge. So this would look like this. And indeed, if you look at a case where you've got a particle, a red, positively charged particle, which is at the same position relative to this blue and red center particle, then you are going to observe these two different behaviors. They are following the arrows. Okay. Now the issue is that working with arrows is not that convenient. Okay, and so instead what people try to do is to get rid of the arrows and replace it by some kind of landscape, a topographical landscape, if you will, where you've got a color code that tells you that the this landscape, the topography, if you will, the altitude is the lowest if this is blue, and this is the highest if this is red. Okay, so it's some kind of altitude. Now this altitude is not like an actual altitude. This is the altitude or the magnitude of something called the electric potential. And the rule here is that essentially positive charges always go downhill. So in this particular case, we've got a blue and a red particle which are creating an electrical potential landscape. And essentially, if you say then that positive charges go downhill, then you are going to get the directions of the arrows. Okay, so this enables us to actually get rid of these arrows because we just need to keep in mind that we go downhill naturally. Okay, in the same way, to be honest, that if you drop a ball on a hill, it's going to go downhill. So it's more intuitive, if you will. Now, of course, having these arrows superimposed with this particular color code is not really easy to visualize. So instead, what we can try to do is start with basically with a three-dimensional representation. So now what I'm going to do is that on the left, I'm going to put at the central part, I'm going to put a negative particle, and on the right, I'm going to put a positive particle. And we are going to see how it's affecting the landscape of this electric potential. So I'm going to charge the actual particle, and as I do so, it's equally deforming the actual landscape. okay, this electrical potential landscape. Right, so this is how a particle is going to affect the landscape of the electrical potential landscape, and the rule here is that again you go downhill, or positive charges go downhill. So what that means is that essentially that would look like this. Red positive charges are repelled and they go downhill from a positive charge, and on the contrary they are attracted downhill by a negative charge. Okay, so now let's have a look at something a bit different. Now I take again a positive and a negative charge, and I'm considering this as being the two ends of a capacitor, if you will, or some kind of antenna. So if I actually look at it, then I've got alternating current, and what this is going to do is alternate and change the polarity of this circuit. Okay, so that's what this is I'm going to look at. So far I'm not visualizing the actual electrostatic potential, but now we are going to visualize it. So if I actually put and look at the actual potential, that's what it looks like. Okay, so it actually changes with time, and it goes up and down on the different locations of these two charges. Okay, so that's what an electrical potential looks like when you are at an alternating circuit, at the two ends of an alternating circuit. Okay, but from this, to be honest, we can't see very much, and it's not clear how this relates to anything we've been talking about so far, especially with vacuum and light propagation. Well, it turns out that if you zoom out a little bit, then this is what you're going to observe. So here I've zoomed out and removed, for convenience, the the apparatus, the generator, and the two charges. But what you see here is like the positive charge, and here's the negative one. And what this looks like is like this. So this is simply zooming out. So you see here that what's going on is there are ripples which are going away from the center oscillating location, and that's it. So we've got ripples that are propagating on the electric potential. So this particular description is what we call electromagnetic waves, and this is the most current, at least classical explanation of light. Light is electromagnetic waves. Okay, so when I'm looking at this, I'm actually looking at light. So once we are there, then we can ask ourselves the following. So light then is understood as ripples in a potential field. Okay, so that's basically the best 19th century description of light. But at the same time, does that mean that light propagates in a medium? Okay, so I don't know if you see what I mean. Does that mean that it propagates in a medium? And the question, sorry, the answer to that is kind of sort of, but the medium is not made of matter. Okay, so it's as if it was its own medium somehow. And so the point here is, can we get to remove this potential from a region of space? So I told you that you've got these ripples of the electrostatic potential, and then we want to know whether, well, basically this kind of potential itself can be removed from a region of space. Now, the current understanding of these ideas is that actually no, this potential, this electric potential, permeates the whole of space at all times. Okay, so that's where we are so far with this 19th century interpretation, if you will, or classical interpretation. Now, the thing here is that there are two main issues with this view which we need to address in order to have maybe a better picture of a vacuum related to light. So the thing here is that when you look at, there are historically two issues that were with this particular picture, classical picture. So there is a difficulty to explain consistently, if you will, the glow emitted by heated material. So here this is a snapshot from a forging video on YouTube, and where you see clearly that there is, a shine emitted by material which is being heated. Okay. So you see, well, aside from being beautiful, you see that there is a definite glow to it, and that's related to temperature, and so there was a big problem with these. Now there is a second problem, which is that of the so-called photoelectric effect. So here I'm simply showing an application which can be used for free on the internet, and I've put the link at the end of the lecture. So there was a phenomenon which is as follows. So here you've got a lamp, and here you've got basically a setup with an anode and a cathode. And what happens here is that you can change the intensity of the light. Okay, so as you increase the intensity of the light, then basically nothing happens if you are in the very large wavelength, so low energy light. And there is a slight potential difference between anode and cathode. And then eventually what happens is that you obtain a current that flows. So you obtain electrons which are being ejected from one of the plates and then going onto the other one. Interestingly, without changing the voltage, okay, you can get an increase in the current that is being released simply by changing the frequency of the light. Okay, so this is called the photoelectric effect. Now it turns out that to solve these particular two puzzles, for the one having to do with the glow of a heated metal and that of the photoelectric effect, then what had to be obtained was to use the idea that light was made of particles, also called quantas. So the glowing problem, assuming quantas, was solved by Max Planck in 1901, and then the photoelectric problem was solved by using quantas again by Albert Einstein in 1905. In fact, that's what that's what he got the Nobel Prize for in physics. So the thing here is that the modern view combines somehow the idea of the field picture I've shown earlier. We've got these ripples on the potential and the particle quanta concept from Einstein and Planck. And the way it works is as follows. You've got potential fields exactly as I've discussed earlier, okay? But then particles of light then are expressed or interpreted as being elementary excitations of that field. Okay, so what that means by elementary is that you cannot have anything kind of smaller than this in terms of amplitude and energy. That's kind of what it means. And these particles of light, which are elementary excitations of this field, are what are called photons. At least that's what they are called now, photons. So on top of this, you've got that all of it is expressed in something called quantum mechanics. Okay, so I'm not going to enter into any details whatsoever on quantum mechanics. This is it would take a whole public lecture or more. But what I want you to at least take on board is that quantum mechanics is inherently a probabilistic theory. Okay, and so what that means is that numbers are never definite. They have this opportunity to change, if you will, in time, or at least upon repeating measurements. So here we've got vacuum 1.0. You've got a particular vacuum that you've emptied of matter, and then you've got no particle of it once you've emptied of matter, and then you basically the state of the light itself is kind of undetermined. Okay, you've got simply light that goes through it, but that's it. You can't really address or talk about empty this region of space of light. Okay. So here we can try to have a new definition of vacuum, where we would have like a 2.0, for example, where we have indeed no particle of matter, but then we also have no particle of light, okay? And so if we have no particle of matter and no particle of light, it means that there is a form of excitations which are not there, okay, which are the minimum ones that can exist in terms of so-called excitations. But at the same time, we need to keep in mind that the whole thing is probabilistic. So what that means in practice is that although on average you're going to have a flat potential, electric potential, is going to fluctuate the potential itself about this zero value. And this is actually going to look like this. So that's, in my opinion, one of the best kind of visualization that I could provide on this. So that's what a quantum vacuum would look like in a cavity where you somehow are able to isolate this particular vacuum. Okay, so these things would be a representation of this vacuum 2.0 or a quantum vacuum. Now, once we have seen this, does this ever bubbling vacuum appear empty to anyone here watching this video? Well, it turns out that maybe not, right? If you see this thing kind of moving around, etc., it doesn't seem that empty. But you could also say, and rightly so, or legitimately so, that it could also be a mathematical artifact, where this bubbling basically occurring in this vacuum has no effect on experimental data. And then that would be more like a philosophical concern, whether this is actually real or not. So to address this particular issue, what we can do is try to look at what is the definition of a vacuum if we go back to the, some of the founding fathers of this idea. So here I'm going back not too far, but to Newton. And what he says here, I'm not going to try pronounce it in Latin, but it's like vacuum. I call every place in which a body is able to move without resistance. Okay, so that's the definition, according to Isaac Newton, of what a vacuum is. And what that means here is that there is essentially, you can probe whether you've got a vacuum or not through basically its mechanical impact on motion. So the problem here is that there are experimental evidence that there is such a thing as quantum vacuum friction. And here I'm just highlighting one of the parts, is that the quantum vacuum, you see in the abstract, may in certain circumstances be regarded as a type of fluid medium or ether exhibiting energy density, pressure, stress, and friction. So by Newton's definition, then the vacuum I'm talking about, so the vacuum 2.0, does actually even provide friction and then resistance to motion for certain objects. So that's the first aspect of it. Now, here, this is another one here that there is on top of it. This is a paper from 2011, that observation of the dynamical Casimir effect in a superconducting circuit. So that's basically an experimental evidence of what was before a theoretical claim that this could lead to friction, pressure, and all that. So this is an experimental here, evidence of this. So it seems to be actually more complicated than it looks, isn't it? And there is a further case as well. So you see that there is cases where you've got a pressure difference in air, and that can have devastating or very dramatic effects on objects. So for example, here, this is a very well-known case. You've got a tank, and the tank is actually being emptied, or is actually empty of its air content, and is simply crushed under the atmospheric pressure. Now it turns out that there is a similar effect which is being predicted in a vacuum. Okay, so in a quantum vacuum 2.0, there is this kind of pressure effect being expected. So this is what is called the Casimir effect. Here you are represented two plates, so it's a side view. You've got two metallic plates that are there, and it turns out that the vacuum pressure is supposed to be larger from the outside than from within, okay, this particular slab. and so this pressure is caused by the bubbling, if you will. And so the bubbling is supposed to be larger or more, with more magnitude outside of the plate than inside, and as a result you get a higher pressure. Now again, here this is just one of the many papers that have been published on this particular topic, where there is a measurement of the Casimir forces between basically some structures, some matter content. So again, here there is vacuum between them. These things are obviously not charged, those are not like attracted or repulsed by simply being charged. It seems to be interpretable as due to the vacuum pressure. So from these things, what we can say as in terms of closing comments is that quantum vacuum, as far as we know, is the most empty state we can theorize in our current contemporary physics, and where the two gents I presented initially would agree on. Okay. Now there are conceptual expectations. It fails, to meet conceptual expectations, so that it's basically empty. And in fact, we've seen it with some kind of bubbling substance or stuff that is bubbling, even in the best case of emptiness, if you will. We've seen as well that there is phenomenological expectations of an empty region of space which are not met by this quantum vacuum, because experimentally speaking, there is both resistance and pressure being exerted by the best vacuum we can think of. Okay, so as a result, with regards to our initial question, if we take away all that can be removed from an isolated region of space, is there something left for physicists to talk about? Well, the answer here seems to be yes, or at least is leaning to a yes. Now, does that mean that this is the end of discussing kind of emptiness or anything like this? Well, it turns out that depending on the traditions and culture you look at, empty means something very different. So, for example, in Buddhist traditions, which is of course quite far away, to some, from quantum mechanics, empty means something very, very different, where instead, as let's say put forward by Friedrich Capra in his book, quite at least popular book, The Tao of Physics, where he makes links between quantum mechanics, for example, and Buddhist tradition, then he actually says, well, look at the current definitions. In the sutra says form is emptiness and emptiness is form. The quantum vacuum is truly a living void, pulsating in endless rhythms of creation and destruction. And that's the kind of things that emptiness means in Buddhist traditions. So I leave you with this. I do not know whether obviously this is the end word about it, but hopefully this will make you think about it and maybe read more on it. So I thank you very much for your attention. And if you want to have a look at the actual content where some of these images or articles have been taken from, then here are for the images, and these, so that's still for the images, and this is for further reading if you want to. Right, so I hope you have enjoyed this lecture, and I hope you're going to enjoy the rest of the lectures we will provide with the University of Lincoln.